Um, okay, good morning, good evening, everyone. I'm Johnny Zhang. I'm a professor at the Notre Dame University of Notre Dame. Today, I will talk about how to do EEG data analysis using R. Um, so I'm going to use this web page as my slides, as I'm going to show you some code during the workshop. Okay. Um, so this workshop is mainly for people who kind of like already familiar with EEG, but not very familiar with how to do the data analysis using R. So I will start with a brief introduction of what the EEG is, and then I'll talk about how to collect EEG data. And I will focus on the EEG data analysis pipelines, including how to do like filtering, downsampling, how to do bad channel detection and removing, and how to do independent component analysis. I will also talk about how to form epochs using EEG data, and then how to analyze this kind of epoch data. Finally, I will talk about the ERP data analysis, particularly using some statistical methods such as t-test, um, linear mix effects models. And you should have received the markdown file I'm going to use. So this is the markdown file I'm going to use during the workshop to do some demonstration of the data analysis. Okay. And if you haven't received it yet, you can let Japon know. Maybe he can share that with you. Okay. Um, so what is EEG? Some of you may be already familiar with this, but basically it's called like a non-invasive way to record electrical activities in the brain. So basically, we put some small sensors on the head of a person. So those sensors are also called electrodes. And with the electrodes, we can measure like the changing in the voltage on the in the head. And this can be used as the indication of your brain activity. And those signals we collect usually very small, is in microvolt ranges. The EEG data is useful for studying both normal brain function and neurological disorders. Um, a very key advantage of EEG is it can have very high temporal resolutions, so we can track the changes in brain activity over milliseconds. So therefore, we may have a lot of data like collected over time. Um, Although EEG has lower spatial resolution than the imaging methods like fMRI, however, because we have like very long time series data, we can actually study like changes um, relatively easily or better than MRI. Because for MRI data collection, you can collect data with very low time resolution. This method is particularly useful for studying fast changing processes like sensation, attention, cognition, and sleep. Uh, it also used like in clinical applications, like we can do like a epilepsy assessment in, for example, even in the hospital settings. To collect EEG data, we need several things, kind of like we need devices to do that. First, we put a small sensors, as I mentioned earlier, it's called electrodes. So those sensors are placed on the scalp of a person. So these electrodes can be used to detect the signals. And those electrodes are often placed on the scalp in certain uh, standardized way. So in this case, we can ensure like we can compare the data from a different person. I will talk about more on this earlier. And the electrodes, oftentimes we use conductive gels and saline solutions. So those can improve the connection between the head and the sensors. So this can help to get better signals from people. And typically the electric signals are very weak. So therefore, oftentimes we use some amplifiers to amplify the signals to better record the signals. And then we can convert like those signals to the digital format so we can save the data and use it in the future. And although the older system oftentimes need to use wires like this, but now there's also wireless sensors, so makes it more convenient to collect data. The data collected are often stored in digital format. There's different common types of EEG data formats. For example, you may see like the files with the extension name period EDF dot set. So this is European data format. The set data format, if you have used MATLAB, we know like this is often used by MATLAB. And also there's a very popular software program called EEG Lab. It was developed based on MATLAB. So therefore, this format is quite widely used. Uh, those data files often contains both the raw time series data from the electrodes. So those measures the raw voltage uh, of the brain activity. And oftentimes we also have some other metadata. So the metadata can tell the locations of the electrodes and sampling rate, like how frequently you collect data, and even the marks. Even the marks means like sometimes we give a test to participants during the data collection. So this type tells at what time those tests was conducted. Um, as I mentioned earlier, like EEG data often time series data, and also from multiple electrodes at the same time. Okay. So for each electrode, we have a time series data, that tells us the voltage changes over time. It often sampled as a very high frequency, like 250 to 2000 hertz. So this means like uh, we record the data like, for example, this means like 250 times a second. So therefore, we can have a lot of data. So the raw EEG data can be stored as a two-dimensional matrix. So on the rows, so those are the different channels. Each electrode can be called a channel. Okay. So for example, if we have 64 channels or 64 electrodes, so we would have 64 rows. And on the columns are the number of times we record the data. For example, if we record the data at 500 hertz for 5 minutes, so in this case, in total, we would have 150,000 columns. So this is calculated as 5 minutes is each minute of 60 seconds. So we have a total of 300 seconds. For each second, we have 500 data recorded. So in total, we have this amount of data. So this is only for 5 minutes of recording. So if you have longer experiments, we would have a much larger data set. Okay. So the example data set I'm going to talk about um, is about is more than 40 minutes. So therefore, we have an even larger data set. As I mentioned earlier, oftentimes we have meta information. So those meta information can also be saved. Um, One like a very important part of the EEG data is the event markers or the triggers. Those event markers or triggers would store the information on the timing of stimuli presented, also like time the participant responses. For example, like during the experiment, we may display a picture, right? We may ask the participant to do something. Okay, so the time the picture is presented will be also recorded, so that we know like when the picture is presented. So if we need the response from the participants, we can also record uh, the time the participant responses, so we know when they makes make the response. Okay. With these event markers, we can link the time series data to some like specific points or specific time. Those events, markers, or triggers are often used to segment continuously into epochs. I will talk about epochs like sooner. So, which means, so for example, if we give a stimuli to the participants, we can pick the data around that stimuli and then form that part of the data as the epoch. Okay. And particularly, the epoch data can be combined or averaged to compute something called event-related potential data, ERP data. And this ERP data is often used to do some more advanced data analysis. Advanced not means like more difficult, it's about to answer like a different question other than the analysis of the time series of the EEG data. And beyond like measuring the brain activities using the electrodes, oftentimes we also include some like auxiliary electrodes or channels. So this can be used to capture some other non neural information. For example, we can capture the eye movement. We can capture like the uh, heart rate of the participants. This signal can be stored as the uh, as other like brain activity data because they are also recorded like by the same time as the other data collected. Uh, um, to help like standardization of the EEG data analysis or EEG data storage, oftentimes we follow certain um, protocols. For example, one of the widely used like EEG data structure is based on like brain image data structure. So this is not just for EEG data, it's also for MRI and other types of data. But basically, this structure includes like necessary information for us to store the data properly. So when people see the data structure, they will know exactly what kind of information they can find. And this also help like the data analysis in the future. Okay. And I will talk about more on this later. Okay. As I mentioned earlier, to collect EEG data, we need to use electrodes placed on the brain. So therefore, how to place those electrodes can be very important. Okay. There's different like international systems we can use or we can follow to place the electrodes. The earlier system is called the 1020 system. The idea of this 1020 system is we can divide like the brain or the head into different regions, and then based on that, we can place the electrodes. For example, we first found like the uh, several like important landmark on the brain. For example, this could be like one landmark, and this could be another landmark. The Nathan like basically is somewhere like between your nose and your forehead. Okay, and the yin is here. So we can find those 2 points, and then we can divide like the head from the front to the back into different regions. For example, this could be the like, 10% of the total length of from the front to the back, and then in between this is 20%, 20%. Okay, so which means like from front to the back, we can place the electrodes in this way. And from the left to the right, we can also divide our head accordingly. So basically, um, from like left to the right, we can find those 2 markers. Uh, so it's near like the ear canal here. So once we find that, again, like we can divide the data according to 10%, 20%. And then it's kind of like we put a grid on our head. And each like intersecting points here, we can place a electrode on the head to collect data. Okay. Then we can label like electrodes combining like letters and numbers. So the letters basically indicate like the regions of the brain, like a front or the back or the temporal areas, like this. And then we use numbers together with the letters. Okay, and Z means like the middle line of the head. Okay, if you use like uh, all the numbers, it means like a left hemisphere of the head. If you use even numbers, it means right. So therefore, we have labels like this: F7, FZ, F8, uh, and P3, P4. So you already know, like based on the label, you know, like where the electrode is placed. Okay. Uh, So this is the earlier like EEG data collections. We have relatively few like electrodes. Okay, then to collect like more activities of brain, and then we can use 10 and 10 systems, and 10 and 10 systems basically expand like add more like electrodes to the head. So basically, you can think about at the middle um, electrodes between any of the two of the previous like tools. Okay, electrodes. So you add one more. So therefore, the distance between the two is 10% of the total length, either from the front to the back or from the left to the right. Okay, so you just add like a mid like electrodes in between. Uh, so for the 10 systems, oftentimes we can place 64 electrodes on the head. Okay. And the latest version, like 10 and 10 and 5 systems can place even more electrodes on the head to collect more detailed information of each area or each region of your head. So this is a table to list like the letter meaning of each like electrode and where they are placed. Okay, and the location details. I'm not going to go through this, but you can take a look later on. Maybe you are already familiar with this. Let's talk about like the base data structure. As I mentioned earlier, oftentimes like to help like communication, kind of like to help people understand like the data collected through EEG device or other neural image data device. It is recommended to organize the data in certain ways. Okay, the base structure is very widely used. Um, in neural image research. So it's a standardized framework for organizing um, neural imaging data. Okay. So this is a true example, and I'm going to also use the data set for illustration in this workshop. Notice that data are organized in this way using files. Okay, and because if we need to store like information on computers, we need to use files. Okay, so it basically has a uh, structure like this. So we start with a project. So this is the current project. Okay, and the project we may have different folders and different files. For example, we could have a folder called sub 001 and sub 002. So this means subject number one, subject number two, and the subject number three. So therefore, within the project folder, we have a folder for each participant. Okay. And for each participants, we may have different sessions. Kind of like a longitudinal data collection. You collect data like at the beginning of the semester, at the end of the semester. So you have two sessions. If you have sessions and then you have session one, session two, and for this particular study, there's only one session. So therefore, you didn't see the session subfolder here. And within the sessions may within have different types of data. For example, you may have EEG data, fMRI data, and here we have EEG data. Okay, so we create a folder called EEG. And then within the folder, we have the actual files, the data files. For example, this is, we know like the EEG data often saved as a data set data. So this is actually uh, raw EEG signals from the EEG data connection. Okay, so this is one for one person. So we may have other subjects, other participants here too. Okay, and then we may have other files to represent other information I'm going to talk about later. Okay, uh, so we have those kind of like a folder structure. Okay, project, subject, session, and data. Uh, Notice that those are all different kinds of neural imaging data we can use. Okay, and we can also have behavior data too. Um, Oftentimes you will see like these types of files. So previously we talked about folders, and for the files you may have the JSON format data files. For the JSON format, you have a key and values. I'll give you an example later on. And then you may have TSV files. So this is typically a text file to include the meta information or other participants information. Then you have raw data files. You could have like um, images directly, pictures, okay, also like raw image data files. Okay. Uh, for the base data structure, if you use EEG data, your EEG data has to be in one of those formats, like either in the EDF format, uh, or VHDR format, or or dataset format. Okay. The example I should use using this format. Okay. Um, so you can actually download the whole data set from this link. And this data set I'm going to use in this workshop. But if you are really interested in doing some real data analysis, this is actually a very nice data set you can use. You can download all the information to your computer. Notice that EEG data is usually large. For example, for this project, um, it, it is more than 100 gigabytes uh, of data. Okay, make sure you have a powerful enough computer to save the data set. Okay. Uh, then let's take a look at each files. Like the root folder, there's one file called dataset description JSON. As I mentioned earlier, we could have JSON format data. Okay. In the JSON data format, in the JSON file, you can see the information like that. Okay. So it has keys. The key means like the name of the entry. Okay. So this is basically the project name and the values. So this is the values used. Okay. And oftentimes for each project, we have name, but the value could be different. Different study may have different names. And then again, we also have authors of the data collection and other information like funding, um, IRB approve um, and data sets DOI for this particular data set. Okay. So this gives you the basic information. And we also have a Python file for the participants information. Okay. So this basically gives the information about the participants data set. So it's essentially gives the explanation of each column of the data. For example, participants ID and user area R. So this means like learning scale. Okay. Um, CESD. So this depression measure. Okay. So based on the JSON files, here you would see like the basic information about the particular data set, right? What kind of information we have in that data. Then we can go to the participants .tsv file. Okay, so this actually includes like the data, actual data for information for each participant. Okay. Yes. I'll see if I can make it like so. So a little bit difficult to read, but let me see if I have this. I have it here. I hope it's on the same row. But so we basically this is the one row. Okay. So those are the column names. The meaning of each column is given like in this JSON file, right? And then we have each row represent data from one participant. For example, um, the score for this like loneliness for the first participants is 59. Okay, and then we also have age variables. So this the age of these participants is 29. So we know the information. The gender is two. Two means I believe like two means male, but we can find this here. Like one is female and two is male. Okay, so now we can connect the information together. Uh, Before doing any data analysis, it's very important that we understand what the data is, right? And then we can do the data analysis. And then we can also have the task information in the JSON file. So this tells us what kind of task we have. For example, 12 means those are the markers or the triggers, right? Means like the queue showing to the participants. Okay. Um, so this means like the stimuli is kind of like a data connection we have. Okay. Then let's look at the real data subfolder. So the in EEG data subfolder, there are also several files, right? There's one file called like this, the channel information. The channel information usually includes the information about like each electrodes, but here we don't have any information here. Um, just like names and the unit of the data collection, but you may have more information here. Okay. And also like the JSON format tells the basic information about the EEG recording. For example, the task name, uh, the device we use to collect data is quick cap. Okay. As the power line frequency and EEG channels 66, and the duration of the recording is about more than 3,000 seconds. Also, sample frequency 1,000 times per second. Okay, and then we have the MATLAB data format. This data set is this file includes the real data we collected from the electrodes, and we'll read in this data set into R for data analysis later on. We also have an event uh, um, data. Event data means like at what time like each event happen. So we have to see like the JSON file with the explanation of each of those events. Okay, so this means the starting time. So when the event was triggered, so those events are here like this. So 63 means start of the task, end of the task. Okay, and 23 this stimulus. Okay, so this gives the timing of the event. Okay, this is remember this is important because we need to use this information to create epochs in the future. So now we understand like how the data collected, how the data are stored, and then we can see how we can analyze the data. Okay, to do EEG data analysis, oftentimes we need to do a lot of pre-processing. Pre-processing means we reorganize our data, we remove the bad information, and we clean up the data, and then we can use the resulting data for future data analysis. Okay. And in this workshop, I will mainly focus on the use of EEG utilities R package for EEG data pre-processing. We are also going to use like MRE for some mixed effects modeling. Okay. To pre-process the data or to clean up EEG data, oftentimes we would follow the following procedure. Okay. So oftentimes we may need to remove non-EEG channels because those channels are not something related to the brain activity. Okay. Then next we will do the filtering. I will talk about why we do this. And then we can detect bad channels to ICA and remove like um, non-brain uh, uh, components. And because we may remove some like bad channels, we can re-add some information through interpolation. And then we can do epoching. And then we can do basic line correction, and then calculate ERP, and then do the statistical analysis. I'm going to go through like those steps one by one. Okay. Uh, Before that, let's install like the R packages we need to use for the data analysis. Okay. I have sent you a email with the instruction to do this. So if you have done this, you can do the data analysis. I mean, if you haven't done it, it's okay. You can just follow the notes here. Okay. This package is not on current, so it's only on GitHub. So therefore, we have to install it from GitHub. Okay. To install a package from GitHub, you can use the remote package, and within it, there is a function called install on GitHub. Okay. So I basically like make a this package was uh, originally developed by Matt Credo. So but I made some like changes to the package so that it can work uh, with our like workshop today. So therefore, you can also install the package directly from my GitHub repos here. Okay. Um, so using this command, you should be able to install it. But this package also use some other packages you also need to install. For example, it uses our MATLAB to read the MATLAB data. So therefore, you would also need this package. Okay, and it also use ICA for independent component analysis. So you can also install this package too. Okay. And if you use like remote install the GitHub, you need to compare the package yourself on your computer. So, which means you need to have the programming environment to do it. On Windows, basically, you can install the R2's uh, software, and on Mac, you need to install Xcode. And particularly in addition to Xcode, you also need to install GFortune to compare the package. Okay. Um, So you can find like the instructions and information on how to install R tools and Xcode here, following the link. Okay. Uh, if you are using like a latest version of R, basically I also compared the EEG data into the binary files. So which means in this case you don't need to um, have R tools or Xcode to install the packages. Okay, so you can download the binaries from here for Windows and Mac. Okay, and if you use like a Linux or Unix version, uh, it's very likely you already have the programming like environment, so you can just install it using here. Okay, uh, you can click the link and download the files. After you uh, download the files, and then you can install the packages directly. So this will be the link or the location you save the files. Uh, uh, then you set is repos equal to now, which means you are going to you are going to install from your local computer. Okay, so this type give you whether you are using Windows or Mac. And if you are using a Mac, using this file, okay, TGZ. And if you use Windows, the extension name should be .zip. Okay. By doing so, you don't need to um, compare the files yourself anymore. Okay, you can install it like you are using any regular R packages, but from your local computer. Assuming you already installed uh, the packages correctly, then we can load the package using library function. Because I need to do some data manipulation and visualization, I also load a tidyverse package. So we know like package includes ggpos2, include tidyr, and also other like packages for data processing. Now let's take a closer look at the exam data we have. So in this data set, all this uh, emotion processing and regulation task study, we have a total of 148 participants. Okay, those are all health adults. Okay, uh, so the experiment mainly look at the how people use the cognitive reappraisal strategies. Okay, um, so the idea is like this. So the researchers gave a list of images to the participants. And then they ask like either like the participants just watch the picture or give like a reinterpretation of the picture. Reinterpretation means like for example, if they see like a negative image like a sinking ship, so they may encourage the participant to think about things like this. Also, the ship was sinking, but all passengers are safe. Okay, so this kind of like positive thinking, right? So they want like participants to generate this kind of reinterpretation of the negative stimuli. Okay, so the researchers first give training to the participants so that they can successfully evaluate or replace an image. Then the experiment will start. Okay. During the experiment, each participant was given a total of 240 images. Uh, at the same time, the EEG signals was recorded. Okay. So those are the images presented to the participants. Okay. Um, so before the presentation of each image, there will be a 1 second queue. So it will tell the participant to either watch, simply watch the image or reappraise the image. Okay. After that, uh, it will be a 5 second like presentation of the image. Okay. For example, give the image, I tell you to replace it, and the image will be showing for 5 seconds. Okay. And then after viewing the images, the participants will read their arousal and valence. Um, the information was recorded. Okay. This is actually the 2 by 3 factorial design. So we have three conditions: either reappraise a negative image, watch a negative image, or watch a neutral image. Okay. And the content of the image can be either social or non-social images. Okay. So this basic is the process of this experiment. Okay. Starting like giving a cue, either watch or real praise, and then the showing of the image. Okay. For data collection, they used like a 64 channel quick cap. Okay. And the sample rate is 1000 hertz. Okay. So those are the basic acquisition methods, data acquisition methods. So there are 64 channels. So this is the name of each electrode or each channel. Okay, and this is the region where the channel or electrodes were placed. Okay. So I also list like the major uh, like functions those electrodes measures. For example, those SFP channels usually measure executive functioning, social cognition, working memory. Okay. So this, based on the previous studies, we kind of understand um, the functioning of each region of the brain. Okay. I'm not going to go through each of those lines here, so I'll skip this. Several additional channels was or sensors were also placed on the participant head. Like HEO was used to measure like horizontal eye movement, and VEO was used to measure vertical eye movement, and EKG was used to measure like heart rate, and CSR was used to uh, measure like a skin conductance. Okay, and we also see like the event information. So I'm not going to go through this again. So this is how data are organized. It's the same as before. Like within each subject, we have each data, and then we have the four files for each subject. In their original data analysis, the preprocessing, they use EEG lab and ERP lab to preprocess the data. So what they did is they used the first filter the data, and then downsampling and better channel rejection and ICA, and then um, epoching, and then condition averaging. So this is used to create a ERP data. And I will show you how to do those steps within R instead. So with the raw data files, the first thing we are going to do is we need to read the data into R to do the data analysis, right? As we already knew, um, the data is saved in the set format here for this particular data set. You may have other types of data, right? Here is the MATLAB data format. Um, So this package has a function called import set. So you can import MATLAB data directly. So I use import set function. If you have downloaded the data to your computer, you can find it direct here. Okay. So I download the data onto my desktop within this folder. So therefore, when I use import set, I do this. And if you do it on Windows, so because I already prepared the notes using Windows machine. So I set like the folder in the Windows format like this. Okay, so this is basically for the from my Mac, right? And if you downloaded the data from our course website, and you want to try this out, uh, you can just read the data into R onto your computer directly. Okay. Uh, uh, if you have a slow computer, it may take like a few seconds or even like a minute to load the data into R. The reason is because the file is pretty large. I believe like the size of this file is about 800 megabytes. I cannot see it here. But if you take a look at the data on my computer, so these are MATLAB data. Okay, it's about 900 megabytes, so it's quite a large data file. Okay, and you can read the data using this. After you read the data into R, it will use about 1.7 gigabytes of memory. Okay, um, so therefore, make sure you have at least like 8 gigabytes or 16 gigabytes of memory is recommended, and more is better certainly. Okay, because later on, if you do some data, other like data processing, it will use even more um, memory on your computer. Okay. Oftentimes, when we analyze data, if you are going to use R mainly in the future, so what you can do is after you import the data from the MATLAB data file, you can save it as R file. For example, here I can save EEG data uh, as R data set. So in this case, I can use this R data set in the future without the need like a MATLAB R MATLAB package to read the data. Okay, you can work with the data directly within R. So basically, I read the data and save data into R. Okay, R format. You don't have to do it. Uh, so let's take a look at the data structure after we read the data into R. Uh, So using this, I can import the data. If I run this, so it took about like 2 seconds. Um, I don't have enough memory. Let me try this again. I probably don't have enough memory because I already run a lot of data analysis here, but I should already have the data set here. So this data has 1.7 gigabytes, so takes 1.7 gigabytes of memory. So we can take a look at the data. To direct the type of the name, it gives you the basic information about the data set. It's just like any R um, data format. So it gives you like there's 69 channels, the name of each electrode, and the sampling rate, the length of the signals. Okay, we can take a look at the more detailed information about the data set. So you can just use the structure uh, of the data. So the data format is a large list. Okay, so the EEG data is a list. It's a list that includes like different components. For example, it first includes the signals um, components. As we know, to look at the um, components in a list. So those are different components, the signals, S rate, events, channel information, timing. The detailed information is given here. So for the signals, remember like we have 6 channels in total. 6 is for brain like brain activity channels and 5 other channels. Okay, so we have 69 variables. And then we have also like the number of observations. Number of observations basically means like number of data points we have in the data set. And remember, like for each second, we have 1,000 um, values. So in total, is this multiplied by 1,000. So we have more than 3 million like values on each channel. Okay. So these are the signals, the main information, time series information. Okay. Then we have the event information. Event information means like um, what kind of like stimuli we used when like the stimuli was presented and the response like information. Okay, so this is the starting time of the event, and this is based on the time. Okay, and then we also have the channel information. The channel information gives the basic information of each electrode. For example, the name of the electrode. Okay. Um, um, the locations of the electrodes used in different ways. Here we don't have the location information. They are NAs. Okay. And then uh, the time the data was, the signals were recorded. Uh, we also have epochs information because we don't have real life epochs yet. So this give you very basic information. So the whole data set is viewed as one epoch. Okay. So this is the basic data structure of this EEG data. Okay. So I list the basic information here. Okay. If you want, you can calculate like the basic channel stats using channel stats function, give you the mean standard deviation and the variance kurtosis of each channel. Okay. Uh, Here, give more interpretation. I already talked about each um, earlier, so I'm not going to repeat this. Okay. But overall, we know like this is quite a large data set, right? It has more than 3.1 million data points across 69 variables. Okay. And this also have a lot of events information. And the data now can be processed with AR because we already have the data in R already. Uh, as we already saw earlier, there's no electrode location information in the data set, right? Um, but sometimes we need to visualize those positions of electrodes. So therefore, we can add or aggregate the electrode information within R directly using this package. This package saves the electrode locations of popular like um, standardized systems. So therefore, we can add the information. For example, to add the electrode information, we can just use this function. And then this is our EEG data. Okay. Override equal to true means we want to replace the existing information because earlier we have NAs, so we want to replace that. So now notice that we have the position information uh, in this component of the EEG data. And remember, like in our data collection, we have 69 channels. So those are measures like eye movement and heart rate. So they don't have a position in the standardized system. So therefore, we don't have information on this. And CB1 and CB2 are used in the quick cap, but it's not a part of the standardized 10.5 systems. So therefore, we don't have this information here either. We can manually add the information, but since those are often used as references, electrodes, so therefore, we don't really need them. So it's recommended not to include this in data analysis or in processing. So here, if you want, you can include using this, but you don't have to. Okay. Uh, I'm going to give you a quick visualization here. I will talk more on this like later on. Um, so this basic plot of the location of each electrode on head directly. Okay. So this is the positions. Okay. The colors basically represent the signals. Okay. And so the signal values from negative 5,000 to 10,000 mu V. Um, So it's a micro voltage here. Okay. But this gives you the basic information how to visualize this. We'll talk more on this like later on. Now let's see how we can work with this data set. The first thing we can do is we can select particular channels or remove certain channels before we do any data analysis. For example, we may remove like the additional physical sensors before we do the data analysis. Particularly the trigger channel does not include any brain information at all, neurological information at all. We can remove that. Right? The function select electrics, elect, elect, elects can be used to remove or keep channels. Okay. So this basically remove select the trigger channel only. So therefore, after you do this, you will have the information on the trigger channels only. You kind of like remove the other informations. I can quickly show you what I mean here. Okay, so here, if you look at the data set, notice that there's only one channel here. The name is trigger. Okay, the reason is because we only select this trigger channel. Okay. Uh, After we select the proper channels, we can do like some like inspections. Oftentimes we do a lot of data visualization uh, in EEG data analysis. Initially, what we can do is we can check each channel to see if there's any like bad channels or if there's any issues with our data collection. For example, this is a time series plot of channel F1. Okay, we can see like there's a downward like a drift here. Okay, and this often indicate that there's some like signal drift. We'll talk about later. So this is the plot of F2. Okay, uh, we can use any like R um, base functions to the plot. So you can use the plot function directly. For example, I use the plot TS, so means the plot time series uh, to generate the plot here. Okay. Um, Take out the data using the dollar signs from the each components. And because we have a lot of data, oftentimes, if you directly generate data within R, it will take a lot of like memory, can be difficult to display. So oftentimes you can save the um, pictures as files direct onto your computer and then inspect that. So this is what I did. I use save the data as a PNG file and then I open it later. Okay. And you can use very basic like statistical methods to analyze the signals. For example, I can smooth the signals using the lowest function. So this is smooth like a curve uh, of this one. Okay. So this is the plot of all 64 channels. And based on this plot, we can identify like potential like issues with the data collection. For example, if you see like a flat line, so that's basically means there's some issue because there's no change in the signals. Maybe indicate a bad electrode. You want to check that, or you want to remove that before you do any data analysis. Okay. Here I also plot like other channels. This is GSR. It like measures the skin conductance. So this is plot of like heart rate. It's also plot like the eye movement, horizontal and vertical eye movement. Okay. And so oftentimes you may check this to see if there's potential. Oftentimes we look at like potential issues with the data collection. So this is used to like screen the data to identify either like back signals or artifacts or something else. Okay. Assuming like your signals are okay, so which means your device, your EEG data collection device works well, and the signals are valid information, are valid data. Next, we can do filtering. EEG data signals are often very small values in terms of macro voltage. So therefore, it can be easily influenced or contaminated by the noise from different sources. And filtering is actually one way to remove those kind of like uh, non-neural signals from the data because we are interested in looking at the brain image. Anything that not related to brain image should be removed before doing the data analysis. So filtering does exactly this task. And oftentimes we want to remove like a low frequency noise and high frequency noise. Um, the low frequency noise usually means like we remove like a frequency like below zero point 0.5 hertz or below like 1 hertz. And the reason we do this is um, because like brain like signals are often like changing like more rapidly, and they changing very frequently within a time period. If there's a very slow change, it all means that's something else. For example, it could be like body movement, could be like your breath. Okay, uh, so in this case, we want to remove this information. It could be also could be like eye blink. So they kind of remove this kind of information are not really neural information, right? We want to remove this. To remove like low frequency noise, we often use a high pass filtering. For example, one is we can use like detraining methods to remove those um, like low frequency noises. Okay. Sometimes uh, at the same time, we often want to remove like the high frequency noise. The high frequency noise could be like electrical signals. For example, like for different like energy grids, they may use different like frequency. For example, for this data collection, um, they have like 50 ounce like energy like frequency, electrical like frequency, and in this case, they are not real like brain like activity either. We can remove that. For some like more active, for some like movement, like blinking, the school often have like um, they often produce like signals with very high frequency, like greater than 40 or larger than 40 hertz. Okay. So we can also remove like those high frequency noises using methods such as like moving average. Uh, Oftentimes the useful frequency for EEG research is between like zero point 0.1 to 30 hertz. For example, like the frequency between zero point 0.1 to 4 hertz usually relate to like sleep uh, and deep unconsciousness like functioning or information. Uh, frequency between like 5 to 7 hertz usually to memory and navigation like functioning, things like that. So therefore, oftentimes we only keep like frequencies within this range. Okay. So how to remove like frequencies below zero point 0.1 hertz and above uh, 30 hertz? Okay. Um, we can use the different filters. For example, like we can use like FLR or IR filters. Those filters can be used to like um, you can think about like automatically like remove like those very low or very high frequency signals. Okay, but they based on certain like algorithm um, to remove like those signals. And FIR is generally like recommended. Also, like it can be slow, um, less efficient. Okay. To remove to filter the data, we need to decide like the filter order. Okay. Uh, this filter order can be decided using like algorithm automatically, but you can also calculate it. Or you can also like set up the filter order by yourself. So the general recommendation to determine the orders is to use this way. Um, so we first define like the filters like based on the number of cycles um, you want to use. For example, if you want to choose like 4 cycles, right? And then we can calculate like how long it takes um, for the signal to run 4 cycles. Okay. And in this case, if we use like a cutoff like zero point 0.1 hertz, so for each cycle, it will take like 10 seconds. Okay. So you can think about like for your heart rate, like um, how many like seconds it take for you have like a one beat in your heart. Certainly this one is like heartbeat will be much faster than this. Okay. Uh, so therefore, if you decide to use 4 cycles at zero point 0.1 hertz, so in this case you would have a um, temporal window to kind of like wait your signals uh, about like 40 seconds. Okay. So once you decide that, and then you can decide the orders. So the orders basically related to um, related to sampling rate and your um, and the total time of your cycles. Okay. So basically, um, to calculate the orders, we already determined like okay, we are going to use like uh 40-second like period, right, to wait our signals. Okay, so that's the total duration we use in our filter. So that's 40 seconds. So the number of like orders plus one gives a number of like uh, how to see this? Those are the like weights used to weight your signals. Okay, you can have 4 weights. So in this case, you kind of like average 4 values at a time, right? So the number of weights will determine like how you are going to um, weight like your signals. Okay. So this is number of ways related to the orders in this way is equal to order plus one. Okay. So therefore your order is actually equal to the duration of your filter times the sampling rate minus one. Okay. And using our example, we have 40 seconds of duration. So it's 40. And then we have a sampling rate of 1000 hertz. So this is 40 times 1000 minus 1. So therefore, the order we are going to use would be around like 40,000. So if you are going to set up the orders of your field yourself, so this about the number you are going to use. As I mentioned earlier, there's some like mathematical like procedure to calculate the orders and then to do the filtering. For example, uh, the EEG filter function of this R package can automatically determine the orders. So we just set the filter order equal to auto. Or if you want to use our own calculation, this will be like about 40,000, right? So in my filtering, I set the low frequency to be zero point 0.1, high frequency to be 30. So I only keep the signal between zero point 0.1 and 30 hertz. Okay. So if I run this, notice this calculated the filter order is about um, 33,000. So it's kind of like similar to what we calculated. So after filtering, you can see the difference. So this is before filtering for FP1 channel. So it's only for one channel, right? So notice there's like a kind of like a drift here. There's a um, linear or nonlinear increase pattern here, right? Before filtering. So this means like there's a drift or there's like a low frequency signals here. And after filtering, notice our filter data looks like this, right? So we kind of remove like the trend here. Okay. Uh, Using like this time series plot is very hard to see like the frequency, the signals with different frequency, but we can use the power spectral density plot. Okay, so this is before like filtering. Notice that uh, we have like low uh, frequency signals. We also have like high frequency signals. There's a lot of changes. And after filtering, I noticed that um, the signals are mainly in this area, right? And after like beyond the 30, there's like a uh, less power in this like plot. So which means we kind of like remove like the frequency with like remove signals with frequency larger than 30. Uh, so we have done the filtering. So we remove low frequency and high frequency signals. After that, next step, what we can do, we can do is downsampling. Downsampling is not required. You don't have to do it. But sometimes the EEG are recorded in very high frequency. Like for example, 1,000 hertz, like in our example. Although this can capture very detailed brain activities, but oftentimes this information is those high frequency information may not be necessary to identify like important findings in the brains. So therefore, sometimes we can use downsampling. Downsampling can reduce the sampling rate. So in this case, it can make our data sets smaller. So it's easier for us to do all kinds of calculations in the future. To downsample our signals, we need to use a downsampling factor. We can decide the downsampling factor using different method. Okay. For example, this Newton's theorem um, tells us like the target frequency should be at least twice of the highest frequency of the interest in your data. So, for example, if you are interested in start like signals of like 30 hertz, you should have a sample at least 60 hertz. So, which means your sampling rate shouldn't be smaller than this. Okay. Uh, for like different types of data analysis, we may also require like different sampling rate. For example, ERP data analysis, oftentimes we use a frequency, we use a sampling rate between 250 to 500. So this is something we can use. Okay. And in our original like data, we have a sampling rate of 1,000. Suppose we want to like down with our data to be to have a sample rate 240, 250. So in this case, we will down sample our data like by a factor of 4. So we can do that in R directly. Okay. So here are lists like the sampling recommended sampling rate for different types of data analysis. Okay. So you can use this to decide your downsampling factor. Okay. Here I use a factor of 4 to downsample my data from 1000 Hertz to 250. This is before um, downsampling, and this is after downsampling. Notice after downsampling, um, the time series is shorter. It's only one-fourth of this time series length. Okay, so it means like only one-fourth of data was saved here. And you can do this easily using this function within R. So this downsampling factor equal to 4. Okay. Uh, as I mentioned earlier, like sometimes we may have like bad channels or bad electrodes placed on the head, or for whatever reason, like there's some like channels that didn't like produce good quality signals. So in this case, if we include those signals in our data analysis, it may affect our data analysis. So therefore, uh, we should like remove those bad electrodes or channels before we do other data analysis, particularly for independent component analysis. Okay. Um, the typical like claims about the bad channel includes the following. For example, if we have flat or near flat signals, so in this case, maybe like this electrode was not connected very well, so it didn't capture the information at all. Okay. Or we may have a lot of noise or drift. For example, the increasing pattern in the signals. This also means like a very bad signals. And oftentimes we expect like because the electrodes will connect information from the brain regions. The brain regions are not separate from each other. So therefore the signals should be always correlated. If one channel has very small correlation with other channels, particularly the neighboring channels, this probably means that there's some issue with the channel or the electrode. Okay. So therefore, we can use this kind of like information to identify bad channels. One way is just calculate the correlation. Okay. So I calculate the correlation of all the channels. And if a channel is correlated with all other channels with a correlation smaller than zero point 0.4, we may identify them as bad channels. Okay. Certainly, you need to decide the cutoff values, zero point 0.1, zero point 0.2, zero point 0.3, depending on your study. Okay. And there are some automatic procedure to identify better channels. And in this package, the AR faster implement these methods um, in this paper. Okay, so it's provide automatic procedure to detect the better channels. We can use this function to do that, to do better channel detection. Okay. And currently, this function only work for aggregate data. And so in order to use this function, we have to create convert our data to be aggregate data. Okay, because we want to analyze all based on the original data set. So therefore, I basically create an epoch with um, the original EEG signal as one single epoch. Okay. The tricky part is to use this epoch function. Okay. So this is only the data set. And then we need to add uh, the epoch information here. So basically the things we need to change is we need to change the events for the epoch and time. Okay. So I just set this to be 1 for all the events and time is 0 for other epochs. And they also need to change the timings table in this data set. So I set this epochs equal to 1. So this will create a single epoch for the whole EEG data set. And then we can use this to detect the bad channels. Okay. Um, Notice that I remove like the eye movement heart rate like channels because those are not really like um, a neural image like brain activity channels. Okay, so I remove this. So it does again, as I said again, it does like automatical like channel removing. So basically, it identify those three channels as the bad channels: FP1, FPZ, SP2. So those are all the channels placed in the front of the brain. Um, so then we have a set of data after removing um, those bad channels. Okay. Uh, I want to warn you that those uh, bad channel, like automatic bad channel detection methods, may give like positive um, false positives. So which means even though some channels may be identified as bad channels, they may actually represent valid information. Okay. So therefore, after you identify those bad channels using this automatic procedure, you should always like check them like yourself to see whether there's actually issues with the data or not. For example, here I basically plot like the um, channel information here. Okay. So there seems some issues with the data. For example, there's a large drift uh, for this FP1. So it's potentially could be a bad channel. But at the same time, you see like all those oscillations over time. So this also may mean they represent some like valid information. Okay. And for FP2, there's some quite like kind of like rapid like changes at times. So this also maybe means there's some issue with the channel. But also it also seems there's some information in it too. Okay. So you may want to further like go back to your original data and data collection to see whether there's any issues with this, whether you want to remove it. Okay. And if you want to be conservative, you can just remove them here now and then add in the polluted information later on back to the channels. And another thing we often do with EEG data pre-processing is to do re-referencing. Okay. Uh, as we know, like when we collect data, we will basically record the voltage information at each electrode using each electrode. Okay, so the voltage information is actually look at the difference between two electrodes. It's not like just a signal as one electrode. It's often based on the comparison between two electrodes. Right? So therefore, like in data collection, we often choose like a reference electrode. Uh, After we get the reference electrode, so for given electrode, we want to measure the signal. So that's the difference between um, the voltage between like the reference electrode and the electrode we are interested in. Okay. Uh, in EEG data analysis, uh, we can often like change the reference point or the reference electrode before we do the data analysis. And for example, like we may do this just because we want to be like use a standard procedure. For example, like in a lot of data analysis, they use M1 and M2 as a reference electrode. So if we use the same and then we can compare our results with other studies, right? There's a different ways we can re-reference our EEG data. One is like we can use average reference. So basically, we can calculate the average of all channels and then use that as a reference points, and then we can recalculate this the signal information of all other electrodes. Okay, but oftentimes we use like a linked mastoid electrodes. So we use like uh, the signals from the electrodes placed on the um, mastoid bones is right behind the ears. And then we can calculate average of those two electrodes and then use that as reference points and then calculate the signals for all other electrodes. And this actually is kind of like most widely used methods now. Uh, Doing like a re-reference is straightforward. So we just need to tell like which channels we use as references. For example, here I just use M1, M2 as the reference electrodes and recalculate everything. Okay. So after filtering, downweight, and bad channel removing and re-referencing, and then we can conduct like a independent components analysis. I will talk a little bit more about the ICA analysis, why we do it, like how to do it. Um, and the reason we do ICA is um, not so IICA is basically the statistical method. It's not related to, it's not directly developed for EEG data analysis. It can be used for many other types of data analysis. And the reason IICA is useful for EEG data analysis um, is because IICA can be used to separate like signals. Okay. Uh, as when so when we collect EEG data, like in the perfect world, we hope like each electrode can separate the information to the region it measures. So which means an electrode only measures the signals at one particular region, not anything else. But in practice, it's not possible, right? So each electrode basically will measure like a varieties of source of information. Okay, it not only measures like the information in the area we directly uh, placed at. It also measures like the surrounding area, like signals. It also measures any change in your eye movement, your muscle, and even like in the change in the environment. Like for example, the use of electric grid will also influence the signal we captured. Okay. So therefore, the information or the signals we got at each electrode is a mixture of many different underlying processes. Right? It could be like true brain activities. Right? It could be also something else. So basically, ICA provides the way to kind of like separate those underlying processes. Um, so it assumes like, okay, the observed signals is a linear combination of the independent latent signals or the source signals. For example, like eye blink could be like one signal, right? Um, mm, so your jaw movement could be another like signal, and your brain activity could be one signal. So therefore, you have several um, several different source signals. Okay, so the ICA basically try to separate them. Okay, find them. Um, so basically, in ICA, basically, looking for like signals that work together. right? So if the two signals has very high correlation, right? They change in the same way. So in this case, we assume those signals are from the same source, right? But if they change relatively independently, so in this case, they may come from a different source, right? Um, So I see is particularly used for EEG data analysis. The reason is because in EEG data analysis, each source signal may have very clear patterns. For example, I blink. Uh, this shows it links strongly with the activity in the frontal area of your brain, right? The horizontal eye movement will show um like a left and right moving pattern, right? So therefore, each of those source signals or could have a very clear pattern. So therefore, we can use those patterns to identify the components easily to identify eye blink, to identify muscle activities. Um, so the reason we did the filtering and uh, we did um, bad channel detection because those can be influence your ISA results. So therefore, we first remove the bad channels, and then we do ISA analysis. Another reason we do IC analysis is, as we know, the brain signals the signals in the electrodes we collected may include, um, signals from sources that are not related to brain activities, right? So therefore, we want to remove those components and then reconstruct the brain signals for the further analysis. For example, if we identify the signals that's related to eye blink, so we want to remove those information from our true brain signals. So our future data analysis is really about the brain activity, okay, not about eye blink or muscle activities. Um, Let me give you a very specific examples that's to explain how does the ICA works. Statistically, so this is ICA models. So in ICA we have observed EEG data, observed EEG signals. We call the X, right? And then we have source signals. So those are the independent components, the signals from different source, right? Then we observe the EEG data uh, from the latent sources through a mixing matrix. Okay, so the mixing matrix means how we combine the different latent sources together to generate the observed signals. Okay, so basically it's a linear combination of the signals. So we use A times S. So this is the true signals, true independent source signals, and combine them, we get the observed signals. Okay. The true signals may contains a real neural information or some artifact. Artifact could be eye movement, heart rate, or some other information. Okay. So basically in ICE data analysis, we basically want to estimate the mixing matrix W. So what the mixing matrix W does is through W we can transform the observed signal back to the true components. So those is the latent signals, right? In the ideal world, if we can separate this very well, our unmixing matrix should be the inverse of the mixing matrix. Okay. So in this case, which means we can directly multiply by the inverse of A on both sides. So we get the true signals from the observed information. I'm not going to go through the assumptions here because it's not really like help our data analysis. But let's look at the toy example here. Okay. Suppose we have three like latent sources in this example. So the three latent sources could be like S1, just the true brain activity. Okay, so it's a neural activity in your brain. Okay, so S2 could be like the eye blink, and S3 is muscle activities. Okay, so notice that your eye blink like also like have the signals like over time, right? And brain muscle movement also like have the signals over time, right? Um, so we would have like a source matrix like this. So this is your brain active at time one, time two to time six, and this is your eye movement um, signals from time one to um, time six, and this is your muscle activity. Okay. Um, so when we collect information through the electrode on the head, so the information basically is a mixture of the three sources of information, and then it generates the time series plot I showed you earlier. Okay. Um, so suppose like we put like three electrodes uh, on your head. So we have three channels. We have FZ, CZ, PZ. Uh, so we have a mixing matrix like A look like this. So this tells us how we mix those signals together to get the signals for channel 1, channel 2. Okay. So for example, this is the width for the first channel. So this will weight the three values here on each column and then get the observed information for this channel FZ. And similarly, the second row will give the signals for the second channel. Okay. And from here we can see like uh, the first channel mainly relate to the first source, and second channel mainly about like the app link. The third channel is more about like the muscle activity. Okay, so we have the information here. And each column A is also called like a scalp map or topography of the channel. So so the observed like EEG data X will be the calculate based on calculating A of S. So this would be the observed EEG signals given the source channels, source information, given the um, mixing matrix here. Okay. So those are the information we actually observe. So this is the only information we know in our data analysis, right? We don't know A, we don't know S, right? We only know the observed information here. So what I see does is it will like I'm mixing this information to get the source information to get the mixing matrix. Okay. So therefore, once we have the um, data X, then we will conduct the ICA. Okay. Um, so to conduct ICA, we basically estimate a mixing matrix. Okay. I talked about how to estimate a mixing matrix earlier. If you are interested in technical details, you can go back. So basically, suppose like we using the algorithm, we get a mixing matrix W. So it's a matrix look like this. Okay. And then we can apply this mixing matrix to our data. And then we can get our independent components. So those is the um, independent components for each source of information. Okay. Uh, uh, Certainly, like here, we assume like we recover this very well. So this uh, estimated source signals is actually the same as the original signals here. Okay, but remember the difference is here. Those are the calculated based on our data. Okay, those are not like uh, true sources we know. Okay. Using those like source signals, we can identify what they are, right? And then we can use different ways to check those source signals to see whether they are like a true brain imaging brain activity information, or it is related to other like artifact, for example, eye blink or heart rate or something else. Okay. Assume like we identify like the artifacts like the second commodity is eye blink. We certainly know this in this example. Um, and we want to remove this eye blink signals from our EEG data. How to do that? So basically, what we do is we just simply like replace all those information in this source signal um, with zeros. Okay. So notice that all of this is equal to zeros, and then we can calculate the cleaned EEG signals by multiply the A matrix to it. Okay. A basically is the inverse of W. Right? Notice that when we multiply this each of these A matrix to here, because these values are zero, so which means in the capital information, in the clean EEG signals, there's no contribution of the eye link to the data anymore. If we go back to the origin calculation. So those are the source matrix, right? So this from eye blink. So if we set this to be zero, so therefore the calculated EEG signals do not have this eye blink information anymore. So therefore we effectively removed this eye blink artifact from our EEG signal. And certainly if you also want to remove those muscle artifact, you can also set this rows to be zero too. So in this case, we remove both artifacts from the EEG data. So if we look at our results, so those are original observed EEG data. So these are the called reconstructed EEG data after removing the artifact. Okay. Notice the values are different. Uh, okay. Then how to conduct ICA? We can conduct ICA using the run ICA function within the package. Okay. And before we do like ICA data analysis, oftentimes because we are only interested in the brain like signals, we can remove like those additional um, electrodes placed on the head with like a eye movement and heart rate. Okay, and because we also identify three bad channels, so we also remove the three bad channels. If we don't remove the bad channels, it will influence your ICA results. Okay. I use the fast ICA method to do the ICA analysis. So the number of components, you can just keep the same number of components at your channels. So this is what I did here. Okay. After remove the bad channels, I have a total of 59 channels, I think. So therefore I use in components equal to 59. Sometimes if you have very high correlation in your signals, you may want to do a PCA first, principal component analysis first, and then you can do ICA. And if you don't, if you want to PCA, you add the PCA equal to, like for example, 20 into this function to do a PCA first. Okay. So this is the output of my IC analysis. So it's very similar to a EEG data like format. So I have a mixing matrix. Now you know like what a mixing matrix is. Basically, it's a matrix, right? Uh, it's 59 by 59 because I have 59 channels. And it also have a mixing matrix, right? So it's a W matrix to get the um, components. And then I also have the components. So the components have the same like dimension as the original uh, EEG data before SA. Okay. Then it has other information similar to EEG like EEG data format using here. So the mixing matrix I talked about earlier, using a three example. Okay, so this is also called like a scalable map or topography of the components. This can be used to identify whether a component is the artifact or not. I will show you an example later. Okay. So how to evaluate the assay results to identify potential artifact? And one thing we can use is we can use scallop map as a visualization method to identify the artifact. And we can also use like a time series plot. It's also called time course plot. And we can also use like power spectrum density. Because, for example, hyperlink are often dominated by the low frequency signals, right? And the muscle artifacts also show, sometimes show like a high frequency um, power for the frequency at the 20 to 30 hertz. Okay. Um, so therefore, we can look at the plot to identify potential artifacts. And another very effective way to identify artifacts is, so we look at the correlation between the components with um, the auxiliary channels, for example, the eye movement channels or the like heart rate channels. Okay. Let's first look at the scalp maps. The scalp maps basically we plot like a um, kind of like the mixing matrix uh, using like the plot look like this. Okay, so it basically shows the signals on the brain. Okay, so this kind of plot can show some information. For example, for the app link, usually you will see like high signals around this area. Okay. And for the EKG, and you may see like a signal pattern look like this. And for eye movement, you will see like the signals on the left and right hand. So it's like eye move like from right to left, left to right. Okay. And so for the muscle movement, you will see like a pattern like this. So therefore, oftentimes we try to identify those like artifact information using plot look like this. Okay. For typical like uh, neural image signals, it should be like spread out like more evenly. So here, those are the scalp maps of all components, 59 components are generated. Okay. Then you can look at over like each of those components to identify potential issues. Like for example, some of the components um, like these components uh, shows those components seem to show like similar to here, right? Maybe like show some like eye blink or eye movement. Um, the regular like um, components like this, so seems there's no clear pattern here. Probably it means like Those means like those like valid like signals or neural sources. Okay. And how to generate those plots? We can directly use the top plots. So this should be your IC results. You can select how many components you want to plot. Here, plot like from 1 to 59. Okay. Uh, so in general, like components with smooth circular patterns that shows a clear two-pole separation of energy um, are like um, characteristics of like neural sources. Okay, this means this could be like represents valid neural information. Okay. And some other plot you can use is visualizing methods. You can use time course plot. Okay. So this is the time course plot of the um, components. And for typical like neural information, you would have like plot look like this with some without the particular like patterns. For like a plot look like this, there's sudden changes like here. So often indicated there's some maybe some like artifact. This one. Okay. And this like may also show some like irregular like patterns because there's relatively small and more changes here. Many times we need to combine multiple methods to identify potential artifacts. Uh, for example, like for the first component, if you look at both scalar map and time course, it's stable time course and this front like dipole like patterns. So it's probably like valid like brain signals. For the component two, mainly like in the front and also this uh, flat signals. So this may means like a noise or something else. Okay. Like I blink. So for each component, you could create a table look like this. Again, like we can also use like a power spectrum density plot to identify artifacts. So if like there's like a very large power at this frequency about like below like 4 ounce, so this often means like I blink up, and if we run like 2 hours, this means like horizontal eye movement. Okay, so based on this plot, we can identify different artifacts. I'll give you a plot here. Okay. Look at like this is the power density plot for um, about like 10 components. Okay. So this shows like how much power like at the different um frequency. For example, like those component um so it's because it's very tiny, it's very hard to see. So this is around like 4 hertz. It's below 4 hertz. It's very like a large like power. So this means like maybe some certain artifact. But again, like using the visualizing methods, it's kind of like subjective, a little bit arbitrary. Okay. But what we can do is we can calculate some like other information. Okay. Um, we can also use autocorrelation of the components. As we know, like the real like neural activities often like has like changing like relatively slowly. So therefore, they should have like a um, uh, larger autocorrelation. And if they change like very rapidly, with small autocorrelation, usually means there's something artifacts there. So oftentimes we look at whether the autocorrelation is low at a lag of 20 milliseconds. If it's uh, we oftentimes we can look at like autocorrelation of the signals to identify like artifacts. For example, it has been found like if the autocorrelation at the lag 20 milliseconds is very low, it's often associated with muscle activities. So therefore, we can look at the autocorrelations at different lags. Here I calculate the autocorrelation uh, at lag like 20 uh, for different mm, electrodes or channels. You can see like there's several channels like several components 7, 32 and 42. They have very low autocorrelation at um 20 second 20 milliseconds. So this baby means um those include like muscle movement information could be potential like artifact we should remove. Okay. And another way to detect bad components, look at whether component loading heavily on single EEG channels. So this means the components are only related to one channel. But as we know, like oftentimes, uh, the oftentimes, like a EEG electrodes will detect like information from multiple sources, right? So if it's only related to one of the channel, um, so it could be like uh, it could be like an artifact. Okay. In this R, we can actually directly like do this detection using this function. So this will be give you like the channels here. That's components that's loaded like mainly on like one channel or a single channel. Okay. So we identify four of them. Okay. Um, Oftentimes we know like the artifact is because of the eye blink, eye movement, or like uh heartbeat. So a very like reliable way to detect those artifacts is we can actually calculate the correlation between the components and those like um, eye movement, eye blink channels. Uh, so we have ECG, EKG. For example, like if we calculate the correlation between each components and uh, this is the horizontal um, eye movement. We found like component one and the component two actually has a higher correlation with the horizontal eye movement. So in this case, this probably means like those components are um, like artifacts related to eye movements. Okay, and similarly, we can look at the component related to um, like um, related. So this is related to like heart rate. Heartbeats. So we found that component 2 and component 4 are highly correlated um, with heart rate. So this in this case, those component 1 to component 4 could be like artifacts too. Okay. So this is a visualization of the correlations. Okay. Um, combining together, we can identify those artifacts more reliably. Here we can use Skype map, time course plot, PSD, and the correlations with other like um, uh, with other measures. Okay. So this give like the potential like um, kind of hints you can look at. So you can looking for those kind of information to see whether they are true like brain signal, uh, or eye blink or eye movement or some other information. Okay. So those are the typical like artifact we can identify in like EEG signals. Okay. Um, as I mentioned earlier, uh, this artifact identification is more about like a subjective process. You have to like look at many like of those plots to be able to like effectively identify uh, the components for the artifacts. Okay. Um, Honestly, I'm not like a EEG like researcher. It's actually very difficult for me to identify the artifacts. But oftentimes after I do the data analysis, I show the results. The EEG researchers, they can like help locate the potential uh, problematic components, and then we can just like remove those components later on. Okay. So once we identify all those artifacts, we can reconstruct our EEG signals. So in this case, those are the all the possible artifacts we can identify using those different methods. Okay, I'm mainly using the statistical methods because reading like those um, plots or the reading looking at those uh, s- topographic plots and the time course plots is still difficult for me to identify those artifacts. You may be more effectively um, doing that. But I just use like those like based on statistical methods. Okay. Those are also like potential like artifacts components we can identify. Okay. So next I want to remove those like components and reconstruct the uh, EEG signals. Okay. Um, so to reconstruct those signals, we can use this function. So this is our EEG data analysis. Okay. And then we need to tell which components to remove. So those are the list of the components I want to remove. I build those list of components. You can do this like by hand. Just take out 1, 2, 3, 4, 12, 28. Okay. So I basically like remove those, um, delete like those letters, and then change that into values. Okay. And then I can create a list of components I want to remove. Okay. And now I get a reconstructed like EEG signals. And remember, when you do this, you may want to use the original EEG data. Okay, use your original EEG data to reconstruct your EEG signals. Now I have a data set with 59 um, channels or 59 electrodes. Okay. And remember, like earlier, I removed some bad channels. I removed 3 bad channels, right? FP1, FP2, FPZ, right? Um, so I wanna like add back this information. To add back this information, we can use channel interpolation. So what this means, like basically, you can think about it. You want to impute your missing channels, right? To impute that, oftentimes you can use surrounding like channels to reconstruct the signals. Okay. So here I simply use this function to reconstruct, to add back the missing channel information. Okay. So for these 3 channels. Okay. Now I have kind of have a complete like information. Okay. So we have done all the like pre-processing, and now we kind of have like a cleaned EEG signals. With the cleaned EEG signals, we can do some other data analysis. Uh, One thing we often do is we do like data analysis based on epochs. The idea of the epochs is to we identify the most relative information from our EEG data. And so these EEG signals are more meaningful to our experiments. And then we can um, conduct the data analysis. Let's look at an example. So if we have EEG data information, as we know, we have data from a long time, right? In our example, we have about like 40, more than 40 minutes of like signals, more than 50 minutes of signals, right? But only at a certain time points, we'll do experiment. We'll give a stimuli to the participants. For example, at this time points, we may show the participants an image, right? Ask them to evaluate this image. So this basically the uh, experimental conditions. So therefore, in our data analysis, maybe like only like information here is most useful to us. So because we want to see how brain respond to this stimuli, right? So this part of information recorded here may be like most relevant uh, to our study, right? And similarly, maybe we have a stimuli here, a different image, and then so only this part of signals will be useful. And the signals in between, maybe they are not very useful for our experiment, right? So therefore, uh, the epoching um, is to select like a part of like information or signals from all the signals to do the data analysis. So oftentimes we select the signals like right before the stimuli and sometime after the stimuli. For example, we can define like an epoch window from like a negative 200 millisecond to 800 millisecond. So which means uh, 200 millisecond before the stimuli and 800 millisecond after the stimuli. So this part of the information is the information that is most relevant to our study. So we want to keep this information. Okay. So therefore, epoching so basically is to um, pick the signals around the events, right? Um, so we oftentimes get the signal before and after the events, right? So therefore, so this is the final signal we are interested in. So if you have like many different events, for example, in this experiment, we present participants with 240 images, right? So we can get like those 240 like epochs from those uh, uh, 50 minutes of signals, right? Notice that those are much shorter, right? There's a lot of advantages of analyzing epoching data than the EEG raw signals. First, like it can boost the signal to region to noise ratio, and this is very important. Remember, like we always have some noise in the data, right? Um, so the true signal is always used. The observed signal is always equal to the true signal plus noise. So you have a lot of noise, and then the results may not be reliable. But we can average the epoch information. For example, we may have one epoch here, so that's basically shows the image, right? And then have another epoch here, shows this image. Both maybe like both are like non-social images. They are about the same types of image. So therefore, I can average the signal here with the signal here, right? And by adding the information up, average that we can reduce the noise in the resulting information, right? For example, like for one experiment, we may have 50 trials, and then we can average the information from those 50 trials, and then we get much reliable signals uh, for that uh, for that epoch. Okay. Then we can also do like a targeted artifact rejection. And remember, like previously, we do um, artifact rejection or bad channel removing based on all the information. And now we can just look at each epoch. We can look at each epoch to see whether they are um, bad channels, bad signals or not. So in this case, if we have 50 trials, we have 50 epochs, and we don't need to remove the whole 50 epochs. Maybe 40 of them are good epochs, only 10 can be removed. So in this case, we can still keep like partial information for a given participant and for a given channel. And another advantage using epoch is to do like a baseline correction. In our in neural image data, in the EEG data collection, there's no true like signals, right? So the signals are always relevant. It's relevant to the reference points. So if we use epochs, so we can start from negative 200 milliseconds. So we can use the information at the negative 200 milliseconds as a reference point, right? And then we can uh, recalibrate the signals here based on that. So you can calculate the difference between the signals here and the signals here, right? So therefore, we can do baseline correction. Okay, so the difference is basically the change before and after the participants seeing the stimuli, right? Based on the epochs, we can compare like different experiment conditions. For example, we can compare the watch condition with the real process condition in the current data set. Okay. So how to create these epochs? To create the epochs, we can use um, this epoch data function. Okay. So in this we first get our like clean data set after I see, and then we can create epochs around each event. So therefore we can identify the events first. So this is what I did. I get all the events from the EEG data. Okay. So this is all the events. I have in total I think I have 19 different events. Okay. Uh, so you can tell the time period you want to use to create like the epoch. So here I use like a negative 0.2 second to 5 second. So which means negative 2 second um 2.2 second before the event and 5 seconds after the events. So this part of the signals will be used to form the epoch for each event. Okay. And my baseline would be from negative 0.2 second to 0.2 second. So I can do a baseline correction. Okay. Uh, by doing this, I basically form the epoch data. So in total, I have more than 14,000 epochs. The reason I have this amount is because remember, right, I have 19 different events. And also for each person, I have 200 40 like image presented. Like at each image, there's a epoch there. Okay. So now I have like this kind of information. And with this, I can then do uh, artifact detection. So I can remove some bad um, epochs. Okay. So I can use the same function here to remove like epochs. So now it removes like epochs based on um, each epoch instead of the whole instead of the whole uh, whole electrode or whole channel. Okay. With the epoch data, I can analyze the data. So first we can visualize the data. For example, this is called like a butterfly plot. It's a plot of each um, channels based on the epochs. Okay, if you don't like select each epoch, so it will basically do the plot for the average of every epoch. Okay, so this is the plot of the each channel. So notice that this is time zero before um, the before the stimuli, after the stimuli, before the event, after the event. Okay. You can also like select a um, um, particular uh, electrode and then plot like uh, each individual like event. So for example, this is plot of FP1 electrode for each event here. Okay, event 2. Notice the event 18. So this is view. This is the watch condition, I believe, and this is the changing condition of the experiment, which means like this is put condition participant just watch the image, and this condition when the participant need to do like a praise of the image. Okay, so we can see the difference here for the epoch. We can also visualize this data used on the Skype using this. So now we can generate like a topography based on the data. Okay, and this is based on the event 18. Event 18 is a real praise condition. Okay, so so this is the condition we repraise the image. But this seems like there's still some like artifact, like app link maybe artifact here. And this is the condition like 19, the watch condition. So basically, you can compare the two plots to see whether there's any difference in terms of different experiment conditions. And we can also do like some data analysis. For example, we can do some statistical data analysis in addition to the visualizing earlier. So here, basically, another plot. We don't have much time, so I'll do this very quickly. So those are just plots. So we can also do a t-test to compare the two conditions. For example, here, I do a t-test to compare the watch condition and the reprise condition for the epoch data. What I did is I get the maximum value of MP1. I just want to see whether the maximum MP1 value differ from each other or differ from each other. So here means like they don't differ from each other. So if you go back to here, so this FP1, right? And this is 18 and 19. So basically I get the maximum of this value for each epoch. And then I do a t-test. So this is what I did in the data analysis here in this t-test. So this basically means like the neural response uh, to the two different conditions are about the same. So if you use the maximum FP1 as a measure, so if you use other electrodes or other channels, you may be able to find the difference. And just for this electrode or channel, we didn't see any difference. Okay. Mm. So for the epochs, we can do this more data analysis certainly. Uh, um, Next, we talk about the ERP data analysis, even related potentials. Okay. So ERP data analysis based on the epochs. The difference between ERP data analysis and the epoch data analysis earlier is in the epoch data analysis, we can look at the individual trials. So which means we can look at the signal change for when they view each image and each experiment. For the ERP data analysis, ERP database is averaged epoch data. For example, uh, For each participant, they see like 250 images, right? So maybe like 80 is like social images. They don't need to like replace. Then another 80 maybe like social images they need to appraise. Actually, only 40. So in this case, we can average the epochs um, for them together, right? So for example, this may be like a first image. So we have an epoch here. So this second image, we have epochs here, right? And this is third image. So what we can do is we can average those three epochs together. So this is for the one types of image, right? And then for another type of image, it could be here. So we average that out for these other types of image, right? So therefore, we would average them, get the average uh, epoch data. And then we would have ERP data. Okay. So the difference is for epoch is just one trial. For ERP, it's like average. Okay. And for the epochs and each condition, when we have many different epochs, like for example, we have 40 images, we would have 40 like individual epochs. For ERG, we only have one. Right? Each epoch may have more noise than the ERP data. Okay. For both, we logged to the event or we logged to the stimuli. Okay. So therefore, to get like ERP data, we can simply average the epoch data. So now we have um, the ERP data. Okay. So now we have got the ERP data for individual participant for the first participants, and we can do this all together for each participants, and we can get the ERP for each participant. Okay. On the website, we download the data here. Notice that they already have pre-processed ERP data. So it's here in the derivatives. So this pre-processed ERP data, they have the pre-processed ERP data for 147%. Okay. So save some time, just directly use their pre-processed data to be consistent with like other data analysis. Okay. Um, so those are the pre-processing steps. Okay. I have showed you all those steps earlier, right, in how to do this in R. Okay. Uh, but in this ERP data, they have averaged all the epoch data. So which means you don't have trial by trial data. If you want to analyze trial by trial data, you can follow the steps I showed earlier. Instead, average them out. So you basically can save the information for each person using this, now then combine them together. Okay. So I'm going to load all those ERP files and then combine them together. Okay. So I upload this data file onto our course web page. So if you are interested in ERP data analysis, you can directly load this data set. So you don't need to process their individual files anymore. So we have like a ERP data for 147 people. You can get like data for each one here. Okay. Um, so in there like data processes, they calculate like other information. For example, the original six conditions are these. Okay. So it's a non-social image, a negative image, and a praise condition. Okay. So this is a neutral social image watch condition. Um, but they also calculate the epochs for other like kind of like event condition. For example, for neural image watching only, negative image watching only. So basically, it's a combination of like the previous like results. Okay, combine the combination of watch conditions, combination of like non-watch appraisal conditions. Okay, so for our analysis here, we should only focus on this. So unless you are interested in the derived conditions, okay. They also have conditions like this. Uh, mm, they also have conditions. Um, uh, um, I didn't include that. So basically, they also have the conditions, epochs for the conditions. You look at the difference here. Okay. So they calculate the difference between the signals of these two conditions, right? So if you are interested in that, you can look at that. But here, let's just focus on the first six. Um, so you can analyze any subsets of data. Um, so this is used to select electrodes, and you can also select epochs. You can also select participants if you want. We don't have enough time, so I'm going to skip this part. Um, Oftentimes when we have ERP data, we often want to analyze the data. We often want to analyze that with other information like a behavior variables. So therefore, oftentimes we want to combine our EEG or ERP data with other information. Okay. So here I first convert my ERB data into a data frame, and then combine the data frame ERB data with the behavior data. Okay. Um, you can do this like very easily using like as data frame to convert ERP data to data frame. Okay. You have to use the updated package. So notice that now I have a data frame has 75 variables and with those number of observations. And in this data frame, I have all those channel information. So this information for each channel. And beyond that, I also have the epoch information, participant ID, and epoch labels. Participant ID is because now I have 147 people, right? So there should be like 147 different IDs. Okay. Uh, I also add conditional variables to my data frame. The reason is notice that um, it has like a non-social changing, but this also has band as CR1. So those are the different kind of condition. You don't have to have this, but I just use this like for some other data analysis, like in the future myself. Now, how do we combine the behavior data? As we know, the behavior data are saved in this file for each individual participant, right? So we can then read the data information into R. So I use read CSV to read this TSV file. So now I have participant ID. I have measures on each variable. So I also have gender, age information. Okay. So now I have this information. This only have like 148 observations. But the previous we know we have data here, right? So what I'm going to do is uh, so this is my ERP data. So I need a link. So this is subject one, all subject one with a lot of this information, right? So for the behavior data, I want to like link each behavior data here. So I just repeat the behavior data. Like for example, this could be age 20, uh, age 20. Okay. So in this case, I will create like a large data set, right? Uh, with added added like columns to represent the behavior data. Okay. So then we have a large data set. Okay. So that's what I'm going to do. So I read in like my participants' data information. Uh, and so this is the meaning of that. So I will use a merge function from tidyverse to merge my data together. But remember, notice that in my like behavior data, I have a participant's ID is subject one, subject two, right? Like this, subject 001, subject 002. But in my EEG data, I have much longer name like this, subject 01, 6, session 1, task, things like that. So I want to make sure I have the same um, subject value here for the participant ID. And so I can match them. So therefore, what I did is I basically remove the extra part of here so that after that, I will create a participant ID with only subject 001, subject 002, right? Uh, Now I have that, I can merge my data. So this is my original like EEG and ERP data set, right? So this is my participant data set. So I merge by participant ID. Okay. So in my X by X is first data set, by Y is second data set. So after doing that, what happened? After doing that, I now have a data set. So the first part, like to here, remember those are the from my EEG data. Notice this from there to here. So those are my behavior data participants information, right? Now I have a large data set. I can do a lot of data analysis. I also create some other variables for to make it easier for further data analysis. Remember, I have epoch labels like here, right? So this is non-social negative image and appraisal condition or the changing condition. Um, so I split these labels into three variables. Okay, and there's an extra space. I'm also going to remove it. So I trim like the labels, and then I split the labels according to the analyze. I split it into three variables where there's a social or non-social image, right? And uh, uh, where there's a negative uh, or neutral image, right? Condition, whether it's a watch condition or whether it's um, a praise condition. Okay, so therefore, I create like three variables based on this label. Okay, now I have a complete data set I can use for further data analysis. Okay, now my data set has a structure look like this. Um, Maybe it's easier to see it here. So this is my ERP data. Uh, so notice I have three variables created here. Whether social, non-social, negative or neutral image, changing. Changing means like replace, and um, watch means like there's no change. Okay. So now like I have different like variables here. Okay. Now I can do the data analysis. Um, so this is the basic information of each condition. Notice that this is the difference calculated by like difference among those two conditions. We are not interested in this. Okay. We are currently only interested in the original conditions here. Let's now do some basic analysis using some statistical models. Uh, I will show you how to do the data analysis based on uh, P300. Okay, P300 is is a well known like a pattern of brain activity. You can notice this when a person like notice, evaluate, or pay attention to something important or unexpected. So this pattern is found in many different EEG studies. Okay, so basically we will see like a positive bump in the brain activity at around like 300 milliseconds after an event. Okay, um, so which means you will often see like uh, uh, a a large chain, like for example, previous like signals may look like this, and then you may see like just a jump around like 300 milliseconds. Okay. Um, so it's often you can observe like between 300 to 500 milliseconds. So this kind of pattern is called like a P 300. Okay. So now let's analyze this data. Um, so as I mentioned earlier, like I only want to look at like the first six epochs. So therefore, I filtered out the first six epochs using like this filter function. And then I group by time and epoch. And then I calculate the mean uh, amplitude of all participants for simply for visualization because I want to see if I can observe those P300 or not. And then I visualize that use code here. I'm not going to go through the code here because of the time. But now notice that you see like the plot here. So this is for each of the conditions. Uh, and this is the average like signals. You will see like there's actually some like um, increase around some here. Okay, so this is from the 300 millisecond to 500 millisecond, but this peak is actually after already after like 300 millisecond. But notice for most, we actually observe like a jump here, right? So again, like we also observe like those P300 in our data set. Uh, uh, in doing the data analysis, like you can either use like the maximum value or you can use the average value between like 300 and 500. The average value is actually recommended by a lot because the average value can reduce the noise after you taking average. Okay. So now I want to take out the uh, um, P300 average value and then do the data analysis. Okay. To do that, I basically filled out the signal between 300 millisecond to 500 millisecond. Okay. Then I calculate the average for three channels for PZ, CZ, and CPZ. And those are the channels that often we can see like a P300 like easily. Okay. So I basically calculate them for analysis here. Okay. And after doing that, you notice that I have data look like this. So I have a subject, and then it didn't show up here, but I have like three columns here. Okay, so there's average score uh, for the information there. And with that, we can do different types of statistical analysis. For example, we can compare the P300 between two different conditions, real place and watch, using t-test. So based on the results, I can look at few other conditions. I'm only interested in the conditions changing on watch. Here I ignore like the type of the images um, there. Okay. Then um, I do a t-test here based on the conditions. Okay. So that's basically means the mean, the difference between mean P300 for this change and watch conditions. And based on data analysis, there's no difference. Okay. So which means they are about the same. Okay. And we can also use the mixed effects models to analyze the data because we have like multiple subjects, and each subjects we have multiple conditions. For example, for watch and um, changing conditions, for each changing, they may view different like images, like a social image, non-social image. Right? They may view like a neural image, uh, neutral image, or they may view like a negative image. So those could be viewed as different trials. Right? Um, if you keep like each epoch information previously, you can also use like linear mixed effect models to look at the differences too. Okay. I have updated the notes. I'm not sure why it didn't show up here. Let's see. Yeah, my updates didn't show up. Let's look at here. Um, so I will send you the updated slides on the course website too. Okay. So let's look at the first look at the mixed model. So we look at like whether there's a difference between the two conditions. But now we take into consideration of individual difference. So which means each person may have their own baseline, right? May have the baseline like values for the signals. So the first model I'm looking at is this model. So it's a two-level mixed effect model. So beta zero is the intercept, the baseline is a slope. So that's basically the difference between the conditions. But now we add an individual value for each person, B0i. So which means for each participant, we have their baseline value. Okay. Um, so in our case, the beta zero is a mean P300 for the watch condition. Okay, beta one is the difference between the watch and the changing condition or the appraised condition. Okay, so this is the participant specific random effect. So how to fit the model? To fit the model, we use LMER function from the um, LME4 package. Okay, so basically the outcome is P300. So it requires on the condition, but we do have an individual um, intercept. So it's specified by this part. So one means the difference is in the intercept. Okay, so individual intercept for each participant. Okay, then we can run the data analysis, look at the results. So these the results give us like fixed effects results and random effects results. Okay, for the fixed effect results, so this is basically the difference between the appraised condition and the um, watch condition. Okay, the difference is 0.06 is insignificant. So this is consistent with our t-test earlier, but now the results, uh, but now for this data analysis, we consider the individual difference, and previous we didn't. Okay. And we also have the random effects parameter estimates. So this basically is the variance of the B01. Okay. If B01 has a large variance, which means there's large individual difference. So that also means like it's important to include the individual parameter here. Okay. On the other hand, if the variance of this is small, so which means we don't need to use a mixed effect model. We can just use a regular regression model. Okay. And if you look at our variance here, the variance about 18.5, and particularly compared to the residual variance, is pretty large. So this means there's a large individual differences here. So therefore, it's necessary to include the random effects. We can further look at this by calculating the ICC, intra-class correlation. So the ICC is 0.855. It's actually very large. So this again is suggested we should have the individual um, difference. Um, we should use a mixed effect model here. Okay. And in regular mixed effect modeling, it does not conduct a test on whether this variance parameter is significant or not. But for the fixed effects like here, we do have the test like a t-test. So if you want to do a test on the variance parameter, you can use the likelihood ratio test. Use this ANOVA function, random ANOVA function. So this function is a function of the package IMR ER test, which means you need to first like um, install this package to do that. By default, this mixed effect model using the restricted maximum likelihood estimation method. But if you want to test the variance parameter, you need to use like a regular maximum likelihood function, regular maximum likelihood estimation method. So therefore, I change this to be false. And then I can calculate this. Sorry. What this does is, it's giving me like ANOVA kind of test to test a significant parameter. You can think about this method as a way to compare two models. One model is we look at the individual intercept for each participant. Another is we don't have this part. We just estimate one overall intercept. So if you compare the two models, notice that the model with the individual intercept fits much better than the model without individual parameter. So this means we have a significant variance parameter too. This again supports the use of uh, mixed effect models. Okay. I give you like a particular like interpretation of like parameters in this model. I'm not going to like go over them here. And we can fit like more complex models to look at other covariates in our data analysis. For example, we can see whether there is a gender difference or not, whether male and female um, uh, differ in terms of those P300. Okay. Uh, and you can also certainly look at other like um, information. For example, you can also include their like depression scores here as a covariate. But I just look at like one covariate here. Okay. So the beta zero is still the overall mean or intercept. Beta 1 is the difference between the two conditions. Beta 2 is the difference between male and female. Okay. I also look at the interaction between them to see whether like male and female differ for different conditions. and as well as a individual parameter, individual intercept. To fit the model, so this is the model we use, right? We just include the interaction between condition and gender. Okay, again, like individual intercept here. As a result, first we look at the random effects, again, like a very large variance for this intercept. So therefore, the ICC is large. So therefore, it's necessary to use the mixed effect model. And for the fixed effects, so the intercept, we oftentimes we are not interested in intercept. For the changing condition, notice is insignificant, which means again we didn't find the difference between the appraised condition and watch condition. And we also didn't find a difference between male and female participants. Interaction is also insignificant. Okay. And if you want to report the results, you can use something like this. Okay. Uh, we can also look at something else, as I mentioned earlier, with more complex results. I basically look at how this relate to depression and loneliness. Um, um, get the results. I didn't have the results here for whatever reason. So this is the results. And again, we didn't see much significance at all. But this is just for this example. Maybe we have other examples, and other like variables. We may see the difference. We also have a P300 for different channels, different um, electrodes. We can also look at the association between them. So now we look, we kind of like you can think about like you control the effect of one channel when you look at the channel one when you look at another channel. Okay, so this basically at this channel as a um, time varying covariate or the condition varying covariate. So I also add the covariates here. Okay, and you can look at the results. Notice that the P300 are correlated with each other. So this makes sense because they we observe like P300 around the same time for both like channels. And notice after control this, age is a significant predictor. Okay. So this means like all the participants has a slightly larger P300 for this um, for this channel. Okay. Um, so basically like in this like workshop, I walked through uh, a very complete EEG data analysis workflow and solely in R. So which means now you can process the raw data and do statistical data analysis within R without needing any other software. Okay. We talk about like the different structures of the EEG data, and particularly we learned how to pre-process the EEG data. And then we talk about how to do ICA to remove like artifact and reconstruct our EEG signals and for further data analysis. And the data analysis is often based on the epochs. Okay, and EEG data are raw signals, right? The epochs actually give us like more meaningful information for doing data analysis. So therefore, we need to know how to form the epochs. And based on the epochs, we can also form ERP um, information. And previous like ERP data analysis often based on like averaged epochs, but now people often recommend to use like trial by trial epochs to do ERP data analysis based on the mixed effect models. So which means, although in this workshop I only show you how to analyze the average epoch data, but you can use the same methods to analyze trial by trial epoch data. Okay, you don't need to like um, average average in your epoch data. Okay. I hope like this workshop can help you get started to analyze EEG data within R. Particularly for those who are familiar with R but not familiar with like MATLAB or Python for EEG data analysis. Okay. There are also many other R packages we can use for doing EEG data analysis in R. Uh, the MER is a R package that provide a connection to the Python package MNE, so you can actually pre-process the data using Python within R first, and then do the statistics data analysis. And this package is using different data format to save the data and um, to do some like pre-processing. Sometimes you may also want to do some like um, other statistical tests. For example, this provides a permutation methods for EEG data analysis. These are package. We can easily connect this R package with the data here. So the general like data analysis flow is like you can first like process the data and then do all of those epoching, and then you can convert your data into a R data frame because most of the R packages um, were developed based on the data frames. So once you have a data frame, you can analyze the data very easily. And also, like once you have a data frame, you can save your data, and for using in other software. For example, in SPSS, you can do like a mixed effect modeling in SPSS, not necessarily in R. Um, okay. Um, I think I use it all the time, but no, I can be here a little longer if you have any questions.
Thank you so much for your presentation, Professor Zhang. There's a chat, a questions about the materials of the workshop. So they said like they clicked the link provided in the email earlier, but they cannot find the data and code. So can you show them they can
Yeah.
find it if possible?
So, so if you can use like I'll put this in chat so you can save this link. So once you click this link, you should already have a account. Once log in, you can see like the course page look like this. I can send you the notes later and the markdown file later, but I cannot send the data files as the data files are quite large. You
Yeah.
can see like the workshop materials. You can find a list of data set here, and also like the markdown files. The notes I just showed you, I also converted it into PDF notes, so to make it easier for you to read on like your screen.
Okay.
And I also add like instruction on install the softwares, because sometimes it, particularly if you have never compare a package on your computer, you may have trouble to install the packages. But I give you some instructions here too. Okay.
Sounds great. Okay, thanks so much.
Any other question?
Mm, This one is the one I saw. Maybe others still have some questions. Yeah.
You can always email me or email to the mailing list for the workshop. And even in the future, if you need to do like a EEG data analysis in R and you have any question, feel free to email me. Okay. Um, I will put my contact information on this website too, but you can also easily search for my email online. Okay. Okay, and if you don't have any question, I guess that's the workshop for today.
Thank
Okay,
you so much,
thank
Professor
you.
Zhang again. Yeah, thank
Okay,
you.
thank you for joining the workshop. Okay, bye. 拜见，朋